Hello guys, welcome to part 2 of Recursion tutorial video. In our part 1 video, we learned how to write basic recursive functions. In this video, we're going to use the example of factorial numbers to introduce the concepts of head and tail recursion. We're going to discuss the differences between them and why one runs more efficiently and consumes less memory space than the other. So in mathematics, the factorial of a non-negative integer n is the product of all positive integers less than or equal to n. For example, the factorial number of 5 is actually 5 times 4 times 3 times 2 and then times 1. And this multiplication can be simplified as the number 5 multiplies the factorial number of 4, because this part is actually factorial number 4. And there's a special case, which is the factorial number of 0 is actually 1. And this is according to the convention of an empty product. Otherwise, the all factorial number would be 0. So in general, we can generalize this factorial definition to be factorial n equals to, when n is greater than 0, the solution is n multiplies factorial n minus 1. Which is corresponds to this one. And when n equals to 0, and then the solution becomes 1. Okay. To implement this definition in Java code, it becomes like this. Let's write a method, public static int factorial and n, and then to translate this, we use an if statement. So if n is greater than 0, then we return n multiply this factorial again and n minus 1 else, which is this part, and then the value is 1. So this is the Java implementation of the factorial definition. Let's use this number 5 as an example to call this function in the main. Factorial 5, and this should display the result of this calculation, which is 120. So in summary, a recursive function keeps calling itself with a subset of the original argument until a condition becomes false, and then the value of the special case is returned, ending the function calls. Recursive functions implemented like this are so-called head recursion. The drawback of with head recursion is that the completion of one function call depends on the completion of the next. So, for example, the completion of factorial 5 cannot be complete without the completion of this factorial 4, because this whole part is the factorial 5, and then without the completion of this part, this multiplication cannot be complete. Hence, the call to factorial 5 won't be complete and return until fact 4 is complete, and fact 4 won't complete until fact 3 is returned, so on and so forth. And this is because this is still the multiplication operation after each recursive function call. And we know that in programming, each function call at runtime requires an extra chunk of memory space reserved to support the storage for the arguments and return values of the function. Thus, the amount of memory required to run this function rose as a linear function of the number n. If n is small, like this number 5, and then this is not a significant problem. But if n is very large, and then the computer performance suffers because of the large amount of memory space requirement. And fortunately, we can rewrite this recursive function, this head recursive function, so that it does not result in the growth of memory usage, because it will be translated to a non-recursive code by the compiler. And these type of recursive functions are called tail recursion. In the tail recursion, no operation should be performed after a recursive call. And to convert this factorial function to tail recursion, we would have to think of a way of passing the calculated factorial value as an auxiliary argument to the next function call. Then we can update the argument value before each recursive call, and leaving the recursive call as the last step, hence the name tail recursion. To convert this to tail recursion, let's rename this function, and we call it head recursion. Factor rename. So let's call it head factorial. Takes a little while to finish the refactoring process in Eclipse. And then let's write this another function called tail recursion tail factorial. The first argument is the same, but second we take an extra auxiliary argument, and then if n is greater than 0, and then what do we do is that we call this tail factorial, and then we pass n minus 1 as the first argument, and then we multiply n onto this second argument fact, and then when n becomes 0, which is the else, we return the accumulated fact argument. Let's go to the mind and see how we call this tail factorial function. It's coming out this head factorial, and then we call this tail factorial 5, and then we pass an auxiliary argument, which is the value of the special case when factorial is 0. So when the number n is 0, the fact is 1, so we pass 1 as an auxiliary argument to this tail factorial. And let's run this code. Control S, Control F11, 120, which is the same. Although the function looks like it's still called multiple times, in fact the same number of times as the head recursion, it in fact only consumes a fixed amount of memory, because there's no memory space being freezed due to the dependency of one function call on the next. Okay. So in summary, tail recursion consumes less memory than head recursion, and because in tail recursion there's no pending operation after a recursive function call. So as you can see, after this call there's no pending operation, either addition or multiplication. But tail recursion does require an auxiliary parameter. This is the auxiliary parameter, and then head recursion being added to the recursive function in comparison to the head recursive function. And this is because Java does not support default parameter values. If we were writing this in the languages that do support default parameter values, like Python for example, then the extra parameter wouldn't be needed. So from now on in this course, we are going to use tail recursion to write programs instead of using the head recursion, because it's more efficient and then less memory consumption. Okay guys, this is the end of part 2 of recursive tutorial video. Thanks for joining. We'll see you next time.